So this lesson is going to be on heat, internal energy, and calorimetry, and we're going to look a bit at terminology and making sure that we have our language precise in what we're talking about. First thing we're going to look at is what we call thermal or internal energy. I kind of prefer thermal, but your book often uses internal energy, and in some of your homework problems it'll say calculate the internal energy. So those essentially are the same idea, and we looked at this already in one of the sample problems in the last video, where if we know the average kinetic energy of the particles, if we just multiply that by the number of particles there are, then that gives us the total energy content of the motion of the particles. The symbol your book uses is a letter U. I think previously I just wrote like E total or something like that. But U is going to be the symbol for thermal energy. And we also already looked at if the kinetic energy is 3/2 kT, we just throw the N in there, and that's going to give us our total energy. This can also be written as 3/2 nRT, just substituting nR for nk, just like we did in the ideal gas law. So let's look at a couple of examples of the difference between thermal energy versus temperature, because sometimes people kind of think of these as the same thing, but they're distinct, and we need to make sure we know what we're talking about. So let's say we've got a bucket of water. Here's a wonderful bucket, some water in there, and let's say that the water is let's say 80 degrees Celsius, nice and toasty, some steam coming off. I guess it wouldn't be steaming because it's not 100, but anyway, there you go. And then let's say we also have a big bathtub full of water. Okay, bathtub, water in there. I'm a terrible artist, but we'll forget about that. Okay, and let's say that this water is a little bit cooler, 50 degrees Celsius. So if I just ask you which one has the higher temperature, that answer is obvious. This guy here has the higher temperature. But if I asked which one has greater thermal energy, since there's so much more water here, even though it's on average cooler, N is essentially much larger. You're going to have more total thermal energy in the bathtub than you have in the bucket of water. And if you mix the two, energy would flow from the water from the water of the bucket to the water of the bathtub, because it's the temperature that determines which way that energy is going to flow. It's not the total internal energy that does that. Alright, so just make sure you keep those concepts straight between thermal energy and temperature. So for a long time, scientists kind of studied heat, and they knew that there was something flowing from one object to another, and they knew that it was always from hot objects to colder objects. So whenever you have a temperature difference between two objects, then you're going to get a heat flow. And they didn't have the kinetic theory, they didn't understand, so they just kind of, if you've got this hot object here and a cold object here, they kind of pictured some fluid flowing between the two, causing this one to cool off and that one to warm up until they reached equilibrium. And they actually called that fluid caloric. And this was until the 1700s, they kind of had this idea of caloric. And that's where the calorie comes from, the unit of energy. They didn't consider it energy at the time. But in the 1800s, when they were starting to put together the law of conservation of energy and realizing that a lot of these different phenomena were manifestations of the same thing, then people started wondering if heat was actually just another type of energy. And to prove it, it was actually a guy named James Prescott Joule. He was a brewer in England, and he came up with a device somewhat similar to this. And he said, if I've got this weight here that's going to fall, I know how much energy it lost, and so that energy has to go into the thermal energy of the fluid. So we had it hooked up to some device like this that agitated the fluid, and stirring the fluid actually caused the temperature to go up ever so slightly. and he was able to measure that change in temperature and equate that heat flow, or that added heat, to the energy that was lost by the falling object. And so he was able to show that that calories are indeed equivalent to joules, not precisely, but they correspond to joules. So we have this conversion factor. 1 calorie is 4.186 joules. And I'll mention that a calorie with a capital C, which is what they label your food with, this is sometimes called a food calorie. And calorie with a lowercase c is sometimes called a scientific calorie. So there's 1,000 scientific calories in a food calorie. Why they do that, I have no idea. Now this calorie unit came along before we knew it was energy, and it was defined specifically as the amount of heat, because at that point we did call it heat, even though we didn't know it was energy. The amount of heat required to raise 1 gram of water, raise the temperature of 1 gram of water, goes up by 1 degree Celsius. Okay, so by definition, that's what a calorie is. And the imperial unit for heat is the BTU, stands for British Thermal Unit. And it actually is kind of based on a similar thing. It's the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So it actually kind of makes sense, even though it doesn't relate nicely to anything else. And it is quite a bit larger than a calorie. But when you have to pay a power bill one day, not power, a gas bill for natural gas, they actually still use this measurement of BTUs. All right, moving on. So if we have all of this heat transferring from one object to another, actually let me back up, one other thing. Now we obviously know it's not a fluid flowing. We now understand that, thanks to the kinetic theory, that you basically just have the particles in one object bouncing around a little faster than the particles in the other. And so they're going to, if they're in thermal contact, they're going to start colliding with each other. And so that's going to slow down the faster moving particles typically, and it's going to speed up the slower moving particles until they all have, on average, about the same speed. So now we understand what is going on, and we don't have to worry about this idea of some magical mystical fluid that they could never actually see anyway. Alright, so we have heat flowing, which is just energy flowing, thermal energy, and that causes the temperature to change. And it flows until the temperature stops changing because it's equal to the other object that it was interacting with. And the amount by which the temperature changes doesn't just depend on the amount of energy. Oh, by the way, we use the symbol Q for heat. So this here is heat. So the amount of heat that flows, it's proportional to the change in temperature, but it also depends on these two factors here, the mass of the sample. So if I have a little tiny chunk of metal and I have, say, 50 calories of heat flow into that, the temperature of that little tiny chunk is going to change a lot more than if I have a giant metal beam or something, 500 kilograms, I don't know. Then putting 50 calories of heat into that is not going to change the temperature very much. The other thing that matters is what we call the specific heat. And what the specific heat is, I guess it's up there already, but this is determined by the material. So different materials change temperature at a different rate with heat flow. And you might have noticed this even in like cooking. A pot of water takes quite a while to boil and get up to temperature, but if you had an empty pot, that metal, if you look at some common metals over here, the specific heat of aluminum is 900, whereas the specific heat of water is over 4,000. So that means that aluminum is going to get hotter. The temperature is going to change a lot more quickly for a given amount of heat input. So water is has one of the highest specific heats. And that actually has a lot of effects on our environment. If you have ever lived in a coastal region, that's one of the reasons why the temperature is so moderate. They have temperate climates there because the oceans, or I guess by Great Lakes or something too, are able to absorb, I guess it's not too temperate there, probably too far north. Anyway, they're able to absorb a lot of heat without changing temperature very much, or they can give off heat without changing temperature too much. So that kind of dampens or buffers the larger changes in temperature. It also has effects on the the worldwide climate, because the oceans allow for a similar effect worldwide, where they kind of dampen the temperature fluctuations. If we have too much heat, they can absorb that heat. If they heat it up really quickly when they absorb heat, then they wouldn't be able to absorb as much. But because they have such a large specific heat, that means they have a large capacity to absorb heat. Okay. So this is basically all I want you to get out of this terminology. I want you to be familiar with. Temperature, which we already saw last time, is their average kinetic energy. Thermal energy is the total energy. And then heat, if you just have thermal energy in an object, we don't say that that is heat. Heat is specifically the energy flowing or transferring from one object to another. So you hold your hand over a stove, you feel the heat, but that's because the energy is leaving the stove and entering your hand. All right, on to the calculations.